Welcome to your second video from Module 2. In this video we're going to experiment with some of the techniques we used in Module 1's video to try to find the area inside a shape whose interior is presenting us with some difficulties. So let's take a look again at this shape, which is called a parallelogram. A little background on this shape. A parallelogram is a quadrilateral whose opposite sides are parallel. Parallel sides are sides which, if extended indefinitely, would never meet. If you focus on one pair of opposite sides of this parallelogram, try to visualize extending those sides indefinitely and convince yourself that those extended edges would never meet each other. And make sure you can do the same for the other pair of opposite sides as well. If you characterize this feature from the perspective of distance, parallel sides are always the same distance apart. Okay, let's get back to the problem at hand of finding the area inside this parallelogram. So we're going to shade in the parallelogram's interior, which we have done here in blue. And just to further emphasize that we're looking at the area inside the parallelogram, let's erase the edges. So in Module 2, did you notice that the shorter edges of the parallelogram weren't fitting nicely along the underlying grid, and that this was presenting obstacles to finding the area inside the parallelogram? Did you notice any parts of the parallelogram that could be cut out and rearranged so that the resulting shape's interior would have the same area as the parallelogram, but could be calculated using one of our four approaches? See if you came up with the same thing that we did. We focused on these two triangles and noticed that these two triangles have the same areas. So we're going to take advantage of that and imagine cutting the leftmost triangle along the edge indicated. Then we can translate that triangle and imagine a seam joining it along the opposite side of the parallelogram. Let's get rid of our cut and observe that this new shape is a rectangle and that it has exactly the same area as the original parallelogram. More importantly, we can calculate the area of this rectangle using any one of our four approaches, like counting the unit squares. Doing this gives us that our rectangle has an area of 24 square units. And likewise, so does our parallelogram. As we come to the end of our video, we wanted to leave you with an open question. Remember that the formula for the area inside a rectangle was length times width? And we wanted to ask you to think about how you might use that formula to derive and justify an area formula for the inside of a parallelogram. Now, a parallelogram clearly has a longer side that you could imagine associating with the length, but the width of a parallelogram is a little bit trickier. You might be inclined to label this shorter edge as the width, maybe because there's a predisposition to thinking that the formula for the area inside a polygon should be labeled according to the sides on the polygon. But remember, the shorter side was the side that presented challenges to finding the area inside the parallelogram. So, how would you determine the width of this parallelogram? If someone asked you, how wide is this parallelogram, how could you respond to them? Can you use the underlying grid structure to help you identify the width? Use this information and the work we've done to write a formula for the area inside a parallelogram. Compare and contrast the approach taken here with what you've done in your approaches, and be sure to justify the thinking that leads to your formula.